So, we have been discussing the MESFET. We started with the principle of operation, and what we said is the operation of the MESFET is based on the variation of the resistance of the region below the gate, and that variation in resistance is brought about by applying voltage to the gate. So, we have used terminologies VGS, gate to source potential, and VGS has a positive value if it is forward biased, VGS has a negative value, it is a reverse biased. And we also saw yesterday or in the previous discussion that when VGS is when the VDS, drain source voltage, is small, the drop from here to here is small, that is along the channel length is small. This is called the channel, this region is called the channel. So, drop in the channel region is small, okay, and then the voltage across the depletion layer is constant from here to that end, source to drain end. But as VDS becomes larger, current becomes larger. Okay. It is, after all, we saw it is proportional to ID is proportional to VDS and it is linear initially. Now, how long will it be linear? That is what we want to see, and what happens if we keep on increasing the VDS. So, as we increase the VDS, the current increases and the drop increases, and if the drop increases, the potential across the depletion layer changes. Okay. The drop here is appearing across the gate and this channel region, and this is plus, that is minus. So, it is appearing, it is as if applying an extra reverse bias across the junction. When you apply an extra reverse bias across the junction, the depletion layer widens. So, the extra reverse bias across the junction due to the drop in the channel increases from as you move from the source to the drain. So, at this point, for example, near the source end of the gate, near the source end of the gate, this potential across the depletion layer is VBI minus VGS. Okay. I am saying minus because that is the polarity that we are taking. If VGS is negative, it adds on reverse bias. So, if VBI is 0.9 volts and VGS is reverse bias minus 1 volt, it will be 1.9 volts across that. So, when we say VBI minus VGS, we are very clear what we are talking of. So, as you go from here, so let us say it was 1 volt, 1.9 volts we said just now, and if the drop is 1 volt, then the potential across the depletion layer at this drain end will be 1.9 volts. I am sorry, this is 0.9 and 1, 1.9 plus 1 volt, 2.9 volts. So, the depletion layer voltage keeps on increasing from source to drain. How much is the increase? As VDS becomes larger and comparable to the VBI minus VGS. Okay. See, if the VDS is small compared to VBI minus VGS, there is the drop across the channel is minimum, and you will have the depletion layer width constant, and it will be linear characteristics. So, it becomes larger. The potential drop across the depletion layer varies from or increases from VBI minus VGS to VBI minus VGS plus VDS. So, as you move from source to drain, what we are telling that is due to that the thickness of the channel reduces gradually from source to drain. Go back to that curve, the depletion layer voltage keeps on increasing, depletion layer keeps on widening. So, the channel thickness keeps on reducing. So, if channel thickness keeps on reducing, okay, the thickness of the channel reduces gradually from source to drain. Now, we also mentioned in the previous discussion that we assume that the electric field in the depletion layer is in the vertical direction, y direction, perpendicular to the channel, okay, and along the channel direction the electric field is there because VD is there. There is a drop along the thing, there is a field, but that field we are neglecting compared to the vertical field, so that we can apply one dimensional equation for finding out the depletion layer width, because after all voltage across the depletion layer is equal to Q N D into W squared by twice epsilon 0. So, that is the implication of that. This is referred to as a gradual channel approximation. Okay. You can just say that channel is gradually changing. The correct thing is the field is only in the vertical direction. That is the assumption, which holds good when the channel lengths are long. Assuming that Ohm's law holds good, the voltage drop dV across the length dfx. I think instead of keeping on going, I can go back to the diagram. Okay. Just otherwise, I will do, I will draw the diagram here and keep it. So, that is the source and that is the drain. Source and drain. And you have got this semi-insulating gallium arsenide. It can be silicon. If it is silicon, this will be sapphire, silicon on sapphire, total insulator. Then I have the gate here, and I am applying VGS. Polarity is, you have to decide whether it is plus or minus. If it is plus, then it is forward bias. If it is minus, it is reverse bias. I am reiterating it so that there is no confusion about that VGS. So, here if the drop VDS is, we are taking across this, neglecting the drop here, because whatever happens is happening within this region. The gate has control only in this region, the gate does not have any control in this region. So, this, if the drop is more there, if it is 0 drop, nothing applied, depletion is like that. Because of the drop in this region, it keeps on widening. That is what we are talking of. So, depletion layer keeps on widening. Okay. That is the depletion layer. Depletion layer does not contribute to charge, does not contribute to current. So, it is only this region which contributes to that. And if this is A, if that is A, okay, and if this is H at any x, please note we are talking of 0 here and x, and it is L here at this end, at the drain end. 0 is at this end, from that end. It may go beyond that point, we are just talking of this point and that point. Whatever happens is in that region, you are not taking into any two dimensional effects. So, within this region, as we move, let me draw it better slightly, it's all cramped here. That is L, that is 0, and you have got x here. So, what we are telling is, we have to find out the voltage drop across this region and relate it to the current. Same law, Ohm's law, V is equal to I into R. We have to find out the resistance. So, what we do is, take a strip here of width d of x, find out what is the drop across that due to current I d, because current is constant right through, there is no current accumulation. So, find out the drop I d into rho d of x divided by area of cross section, that is all what you are doing. In the previous case, that was this area of cross section was constant as you move from that end to this end. Now, because the channel thickness keeps on varying, reducing, it is not a constant resistor, it is a varying resistance. You can see what happens because of that. So, this is d of x, and what is this quantity at this point x? That I call it as h of x. I am keeping this diagram because I do not have to go back to this slide again and again. That is h of x, and this quantity is nothing but A minus h. Okay. So, the area of cross section to this is, current flow is A minus h, okay, into the depth, depth is W. So, the current I d or the voltage drop d V will be is equal to I d into rho into d of x divided by area. A is the area, and area is nothing but rho d of x divided by w to a minus h into I d. So, that is what we are going to compute. All that we are going to compute in the entire analysis today is compute that current voltage drop due to the current I d, and when you go to reach the drain end, that is equal to the applied voltage V d s, total drop. So, assuming that Ohm's law holds good, the voltage drop d v across the length d of x that we have projected there can be written as follows. I have rewritten that, where d v we said is equal to I d into d of x divided into rho divided by a minus h into w. We have put it there. Now, I am substituting for rho in that equation. I am substituting for rho, which is nothing but 1 by q n d into w into mu. So, let us go back to this now. So, when you go back to this slide, I d into d of x and rho is 1 by q n d mu n, and w, this is the area, and h I put is h of x because it is a function of x. Okay. Now, integrating, now we want to find out what is V d s is. Integrating, we get the total voltage drop. So, all that I have done is I have used the integral term. Left hand side x is equal to 0 to L, because L is the other end of the drain, x equal to L. So, channel is varying from x equal to 0 to L. So, I am increasing it from 0 to L, integrating it. So, this is the term. All that we have to do now is, you see this particular term h of x. H of x is a function of x, no doubt, but it is a function of actually the voltage. More is the depletion layer voltage, more is h. So, this is a voltage dependent term, this particular term. So, what I can do is take the entire denominator to the right hand side, put this sum within the integral, because it is a voltage dependent term, and on the left hand side I can retain just I d into d of x. So, left hand side when I integrate from 0 to L, it is I d into L. I d into d of x, integral is I d into L, and I have taken the entire denominator to the right hand side. Okay? Just see it here. I have taken this entire thing to the right hand side, pull this a outside, you get 1 minus h by a. That is what we have done. Okay? So, this is the equation, and the integral will be of course 0 to V d s. The limits I have not put there. So, I put it again now. Now, let us see what is this term. What we have done is, instead of keeping on writing q mu n and d w a divided by L, see I have removed this L from this side and taken to the right hand side. Okay. Now, I d will be that particular term, a constant of the device q mu n d w a divided by L, I call it as G naught. Okay. And inside this is the particular term. So, what is the G naught? G naught is actually the channel conductance. Okay. Let us go back to that. G naught is sigma, this is sigma into W into A is the area of the channel if no depletion layer is present, full channel open, entire channel if it is open. A is the thickness, okay. A into W is the area of cross section, L is the length. So, G naught is the conductance of the channel which is fully open. It is easy to remember in that particular way, you do not have to worry about what is the thing. In fact, it is 1 over R channel resistance if the channel is fully open. Rho L by A, I put it as L sigma into A by L. Okay. Now, integral 1 minus h. What is h? H and V p 0. V p 0 we have defined in the last lecture. V p 0 is a pinch off voltage, that is the potential that must be present across the depletion layer. So, the depletion layer width is A. Okay. Just recapitulate your memory. V p 0 Q n d into A squared divided by twice epsilon r epsilon 0, and V b I minus V g s plus V of x. What is that? V b I minus V g s is the potential here, plus V of x is the potential there. So, that potential across that is related to the H. So, that is equal to H squared divided by twice epsilon r epsilon 0. Now, you know how to write that H by A. Notice now, hereafter we do not have to rewrite this. The depletion layer widths are proportional to square root of the voltage across that. A is proportional to square root of V p 0. H is proportional to the square root of that voltage there. Divide H by divide by A, you get square root of this divided by square root of that. So, that is what we have done. What we have done is we have divided H by A here, and H is proportional to V b I minus V g s minus H of x, square root of that. A is proportional to square root of V p 0. So, that is simple as that. So, hereafter whenever I write ratios of the depletion layer bits, we will write square root of the voltage across that. For example, the width of the depletion layer at the drain end will be, if I have to write H, V b I minus V g s plus V d s square root of that, drain source voltage. Now, integrate that. Not difficult, looks cumbersome, but it is a simple expression. A simple integral y to the power of n integral is y to the power of n plus 1 by n plus 1. That is what we have done. So, G naught integral of 1 evaluated from 0 to V d s is V d s, and square root of V p 0 I pulled it out, which is a constant. All that we have to integrate is V b I minus V g s plus V of x to the power of half. That integral is whole thing to the power of 3 by 2 divided by 3 by 2. That divided by 3 by 2 is here. Okay. Now, this integral is V b I minus V g s plus V of x to the power of 3 by 2, because it is root of half, okay, and within the limits V x equal to 0 to V d s. So, you can see V b I minus V g s plus V of x becomes V d s at the drain end to the power 3 by 2, at the source end V x equal to 0. So, it is V b I minus V g s to the power 3 by 2. Is that okay? All that we have done is integrated this term V b I minus V g s plus V of x to the power of half, put the limit V x is equal to V d of s at x equal to L, and V x equal to 0 at x equal to 0. That is all what we have done. So, this term will be haunting us for some time. This particular thing we will have to deal with this and modify it to bring it to the shape that we usually see. So, let us do that. So, first thing, how will this particular term will be, that I d versus particular this thing, how will that be? Let us see that. When V b I minus V g s is large compared to V d s, that is V d s is small, that case we have obtained from the first principles in the previous lecture by taking the width to be constant. Now, this must be hold good, and we have to get back that equation if what you are saying is correct. Let us see that. So, we are going back to that linear region. So, we will see whether we get the linear region or not. V b I minus V g s much greater than V d s, and using binomial expansion we get the linear region. Okay. So, what you have to do is, I think I will just quickly do that, so that you are not left with any hang ups on that. So, what we have is okay, I d s, I d is equal to G naught into V g s, V d s, V d s minus 2/3 of root of V p 0, okay, into VBI minus VGS plus VDS to the power of 3 by 2 minus to the power of 3 by 2. That is what we have got. What we are trying to see is when this is small compared to that. Okay. So, that VBI minus VGS if it is much large compared to VDS. That is the case 1 that we are discussing. Expand that. So, ID will be equal to G naught VDS minus 2/3 of root of VP 0. Okay. I will pull out that VBI minus VGS to the power of 3 by 2 into what do you get now? 1 plus VDS divided by VGS. Okay. 1 plus VDS divided by that quantity. 1 plus x, which is x is small, 1 plus x to the power of 3 by 2 is 1 plus or 1 plus x to the power n, binomial expansion is 1 plus n x, taking one term. So, 1 plus, that is 1 plus VDS by VBI minus VGS into 3 by 2 n of x. So, I will write it as binomial expansion using that 1 plus 3 by 2 VDS divided by VBA minus VGS. Correct? What about this term? I have taken that out already. So, I am carrying that minus 1. So, these two cancel, these two cancel, these two cancel, and I will be left with equal to G naught into VDS all cancelled, okay. And this 3 by 2 is cancels with that. I will get VBI minus VGS divided by VP 0 into VDS. That is what we have got there. So, what we have done is just expanded this particular term, binomial expansion, pulling this VGBI minus VGS out, you get 1 plus VDS divided by VBI minus VGS to the power 3 by 2. That we write it as 1 plus 3 by 2 VDS by that. So, that second term we have pulled out. So, minus for these to cancel out. So, it is very simple. Now, what we have written there is we have pulled out this VDS from this inside the bracket, you get it as G naught into 1 minus VBI minus VGS by VP 0 square root into the whole thing into VDS. Okay. So, this is a linear relationship. So, whatever we have discussed now summed up and put here, that is the same expression that we have written there, which is actually G naught into 1 minus VBI minus VGS by VP 0 square root into VDS. This is what we have got in the previous lecture by taking that uniform thing. This is linear characteristics. Now, let us just go back and stop for a while before we write that further equations. We have got the integral. Now, physically what do we expect? So, what we have said now is you get a linear characteristic. From that expression that you have got there, if VGS is 0, you may get a characteristic like that. Linear region means it is flat, very small depletion layer width, area of cross section large. So, current is more for a given VDS. So, if this is VGS 1 and you get increase it negatively, depletion layer widens, we get linear. So, let me not draw a number of curves, let me draw only one curve for one particular VGS, it goes on. What we have seen is, if I keep on increasing VDS, the resistance which was having the same area is no longer maintained. The area is not maintained constant, the area keeps on falling. How much the area keeps on falling depends upon how much is the VDS. So, you can see you have a resistor now. Originally you had a resistor like this with the contact like this. You can see that it is so simple. We are talking of a resistance R there with the channel length thickness equal to whatever was there. Now, when you keep on increasing this voltage, this remains same thing, channel that falls, not exactly linearly, it falls in some fashion depending upon the voltage there, like that, like that. Each increase in voltage as move down here, each increase in drain voltage will make that region, at this point I have the channel thickness varying like that. What happens to the resistance? If I take a resistor which is constant and if I keep on reducing this cross section in that fashion, the resistance actually increases, the resistance increases. So, if the resistance does not increase, ID would increase linearly with voltage. If the resistance increases, ID will not increase as much, it will continue to increase, but non-linearly. So, what happens now is you have the resistance, instead of increasing like that, it would have increased like that linearly, but now it does not increase that much. Non-linearly it goes because this resistance keeps on increasing. Till what time? Till what stage it will increase? Till this region comes in and merges with this edge. Once it merges with this edge, what happens? Supposing it closes the channel completely, what would happen? If it closes the channel completely, current will fall down to 0. If the current falls down to 0, voltage will fall down to 0, but you have the voltage there. So, now you have a situation where it is very tricky. Qualitatively we can understand it. Okay. First, qualitatively what I would say is, when it closes here, if it closes, the current tends to fall. If the current tends to fall, the voltage drop tends to fall. If the voltage drop tends to fall, this tends to open up. If the voltage drop falls, that voltage is reduced, that will fall, it will open up. In other words, what we have is a dynamic equilibrium situation. There will be a small opening left, which will be hitting equilibrium between the voltage drop and this channel opening. Okay. In fact, you will see more to it, more than what I means right now. Okay. But right now, I will say that a dynamic equilibrium is there, where the depletion layer slightly leaves the channel open, so that to let in the current flow and equilibrium between the current and the voltage, both should be satisfied. So, that is what is done here. At that point, once this happens here, the resistance shape is like this, and there is a voltage drop here. What is the voltage drop there? The voltage drop there is such that the depletion layer width is almost close to that. Okay. The depletion layer width should be such that it is almost closing, but still there is a small opening is there. Let us say that is a delta. So, there is a small opening here. So, the depletion layer width you can say almost equal to A. Okay. So, what is the voltage across that? If the depletion layer width is A, it is pinched off at the drainage. You say that channel is pinched off. So, the voltage drop across the depletion layer when this happens is Vp 0, pinch off voltage. Okay. So, that is Vp 0. Now, that is V p 0 and this voltage is equal to, it cannot change beyond that point, because if it falls, it will collapse, open up, but it has reached an equilibrium situation where that is held constant now. So, this is just about to close. So, you have a situation where, please understand this very carefully, you have a situation here where this voltage now remains constant such that this is V p 0. So, what is this voltage now? That is V d S saturation, that is beyond that it will not increase. If this has saturated, what happens to current? We are still working on the theory of the resistor. If this has reached constant and this shape does not change, resistance does not change. So, the current is V d S divided by that resistance. Still we are holding that law into valid. So, V d sat, that voltage saturates, since resistance also is saturated now, current saturates beyond that point flat. So, this is actually V d sat. So, that is the entire concept involved in the IV characteristics of the MESFET, and the model that we have discussed is the Shockley's model, because Shockley was the one, the Nobel laureate. First time he gave it way back in 1952 or so. Okay. So, that model still holds good very well, so long as the channel lengths are not too short. We do not deal with short channel lengths, that very well holds good. Okay. So, now what we want to know is, what is this voltage, how much is the V d sat? We said that V d has saturated, the whole thing is that whether it is correct or not we have to examine later. It is quite correct for most of the devices, where it fails and all we will examine afterwards. V d sat is the voltage at which the channel has pinched off at the drain edge. This has closed down this path. This has come, although it cannot close totally, but almost closing down. The opening is very small, finite. So, the V d sat, how do you find out? That plus B b I minus V g s is that voltage, B b I minus V g s is that voltage, plus V d sat is actually equal to. So, we are talking of a situation where, let me just redraw this now. At saturation, it is almost like that, and this is almost equal to A, and this drop is V d sat, and this drop is actually equal to V b I minus V g s. So, V b I minus V g s plus V d sat is equal to V p 0, pinch off voltage. So, what we are saying now is, okay, we can now look into the analysis. So, the characteristic become nonlinear because the resistance becomes is no longer same, resistance value changes. So, as V d s is increased, I d does not increase correspondingly, it increases less because resistance increases, and ultimately it reaches saturation, the point at which the channel pinches off at the drain end. Supposing it is pinched off at the source end, what will happen? Supposing it is pinching off at this end, you have no chance. It is closed here, the current flow will be 0. So, to make the current flow 0, you must close at the source end. The moment you open it this here, it will let go through this small opening here. Okay, that is the idea. So, turn off the device, you must apply V g s such that it is closed at the source end. Okay, you just block that totally. Now, once you let in the current flow, it has to come out through the drain end, so it will leave a small opening. So, even though it is pinched off at the drain edge, the current is there, saturation current. So, we said I d is nonlinear. Okay. Now, we have plotted that linear, nonlinear, saturation. Now, V g s 1, V g s 2, two voltages are there. What is this voltage at which it saturates? That is what we are trying to find out. Drain saturation current I d s, that is what we are trying to find out is how much is that, how much is this. If you know what is the VDS at, you know what is the current is, because in that equation that we have derived just now, there are only two unknowns, VD and ID. So, once you fix VD sat by this condition that VD saturates when the channel pinches off, you can find out ID sat. So, now what we have been discussing so far, we have put here the ID saturates when the channel is pinched off at x equal to L, drain end. So, we have reiterated it more than once. Okay. So, what is that voltage V p 0 in terms of VD sat? At the source end it is V b I minus V g s, at the drain end it is V d sat, and that sum of the voltage should be equal to V p 0. That is what we have said. So, that is what we have said here, this voltage must be equal to V p 0 and this voltage is equal to this voltage, that is V b I minus V g s plus V d sat. Okay. So, now we are writing that equation. We are back into that equation. I think I better write that equation once on the board, so that it is all the time available to you. That is the general equation. I will just write it and keep it. Because otherwise we have to go back and forth. So, I d is equal to G naught. This equation holds good up to the pinch off point. Once it pinches off, you find I d and V d sat, that is it. Okay, so, let me write down this formula on the board, so that we can just see, substitute for these values. We know now that the current will saturate when channel is pinched off at the drain end. So, we will just write this for a time being, keep it on so that we can use it all the time. E naught into V d s minus 2/3 of root of V p 0 into minus plus so, what we say is, we want to find out the drain current when the drain voltage saturates, drain to source voltage saturates, that is what the voltage across the channel saturates. That happens when V b I minus V g s plus V d s saturation voltage is equal to V p 0. Also, all that we have to find out is substitute for V d sat equals V p 0 plus V g s plus V g s minus V b I, or we have to put V g s is equal to V g s minus V p I minus V p 0, V p I minus plus V p 0, V g s minus V b I plus V p 0. Okay. I will leave it at that. So, what we want to see is how this equation gets modified. Ultimately, we want to correlate it to terms like threshold voltage. Okay. That we will see. Now, let us go back to this equation. So, here we substitute for this quantity V b I minus V g s plus V d s, and V d s is saturated, that is V p 0. Okay. That is what we are doing. So, we keep this as V d sat. So, what we do is that now, that is V d sat, and this whole thing what was there, that is VBI minus VGS plus VDS SAT is VP0 and this quantity. Now, what we do further is just a manipulation of terms. IDS is equal to G naught into, once again I am substituting for VD SAT. Okay. What we are doing is I am substituting for VD SAT there as this quantity VP0 plus VGS minus VP0 VBI. Okay. That is what we are doing there, because everything we want in terms of these quantities. Now, notice that we are able to eliminate VD SAT from that. So, we are trying to eliminate that, put it everything in terms of VBI and VGS and VP0. Okay. So, this is the particular term that we get now. How do we go ahead further? This is a saturation current. We want to simplify this. What we do is we use a term called threshold voltage. Okay. Threshold voltage is the VGS at which the channel is just pinched off at the source end. Okay. Suppose I apply voltage VGS such that is what I mentioned just some time back. You can prevent the current flow, that is just make the current equal to 0, or just allow the current just to start flowing when this is closed here, and this is closed here when the potential drop from the gate to this end is equal to Vp0. And what is that quantity? Vbi minus Vgs should be equal to Vp0. So, when this is Vp0, the voltage across the, there is no drop in the y direction, x direction. So, what you have is Vbi minus Vgs is equal to Vp0. That particular Vgs is actually threshold voltage. So, threshold voltage is the voltage that you must apply to the gate, so that potential drop across the source at the source end is Vp0. Simple, remember like this, total potential drop should be equal to Vp0, and instead of writing Vgs, I rewritten this equation as Vgs equal to Vbi minus Vp0. I put it that side and Vp0 on that side. Okay. And this voltage is the threshold voltage, that is Vbi minus Vp0. Now, you would appreciate why that term I put there, Vd sat is equal to Vgs minus that quantity. Okay. So, let us just go back to this and see. We have just now said from there threshold voltage is Vbi minus Vp0, which means this whole quantity is actually equal to. So, that quantity is equal to Vgs minus V threshold. There is something already written there. So, that is equal to Vgs minus V threshold. So, that is what we are. So, this is exactly the same as that of the MOSFET. The MOSFET, the current saturates when Vds is equal to Vgs minus V threshold, and Vgs minus V threshold is a channel potential drop across the channel. Okay. So, here also that will be potential across the channel. Okay. Saturation voltage Vd sat is Vgs minus V threshold. So, now once we do that, all that we do is substitute for these quantities. Okay. We have written there Vds is equal to this quantity, saturation voltage. In fact, if you see the previous equation that we have written, we have put it as, just let me go back and show you. See, all that we do is meddle with this Vp0 plus Vgs minus Vbi. Okay. The same thing I have written, that is Vd sat minus 2/3 of this quantity. Okay. So, what we have done is just rewritten those terms. Let me just see whether we are, yeah, just see here. The first term is that within bracket you have got Vp0 to the power 3/2, and this is that V I, that is what we have written here. So, I am just gone back to this to show you that we have not changed anything, and then we did this quantity, and then we are just substituting is the same equation, the V p 0 and this is minus this quantity. Okay. So, all that we have done is we have substituted in that equation that we have been writing so far, that V b I minus V p 0 is V threshold. So, that is what we have written. So, here you can see V g s minus V threshold, that is V b I minus V p 0, that comes here, minus the same term and same term V p 0 to the power 3 by 2, and I do not want to put it as V b I, we want to put in terms of V g s and V threshold. So, that is why we just rewrite for V b I here V threshold plus V p 0. So, V b I minus V p 0 is V threshold. So, that is why we are able to write V b I is equal to V threshold plus V p 0. That is all what we did. So, we have got now everything in terms of V p 0, V g s and V threshold. Let us see how it changes. What we are doing is just there is no more concept involved, all the concepts have been crystallized. All that we are doing is just manipulation of this equation to bring into the form that we usually see in the case of MOSFET. So, this rewriting this, again substituting for V p 0 we get V g s minus V threshold, that quantity first term, and second term is retaining the same thing. I just have to go back and forth once. First term is same, second term 2 by 3 root of V p 0, okay. And I pulled out that, what I do is I pull out this, and then it becomes 2 by 3 root of V p 0 into V p 0 to the power 3 by 2 into 1 plus 1 minus whatever is there. Okay. Once again I will go back and come back, I pull this out. So, I will get 1 minus this whole thing divided by V p 0. Okay. Now, let us see how this will work out. So, you have got here 2/3 of into V p 0. What we will do now is to, instead of writing, keeping on writing V g s minus V threshold, we will call it as V g s dash. When I write V g s dash, that is V g s minus V threshold, and this term is V p 0 to the power 3 by 2 by root of V p 0, that is that. And inside this, now you see the whole thing becomes smaller now equation. Okay. 1 minus V g s dash is what? V g s minus V threshold. So, minus V g s dash is V g s minus V threshold, and V p 0 retained. I have not made any changes. So, all that I have done is put V g s dash equal to V g s minus V threshold. So, now you get this quantity here. Okay. How do we simplify this? It is a slightly not pleasant equation to see it, to look at, but we will see it further. I have rewritten this equation now. Okay, G naught into V g s dash minus 2/3 of V p 0, okay, plus minus 2/3 of V p 0 minus minus plus 2/3 of V p 0 into that quantity. Okay. That quantity I am putting it as 1 minus V g s dash V p 0. Simple manipulation, nothing much done. See, once more you have a look at it. This is pulled out, I will have 2/3 of V p 0 into this quantity. Okay. So, that I am taking into inside 2/3 of V p 0 into 1 minus V g s dash by that. I am pulling out that V p 0 from that side. Okay. So, now it looks more bearable, this equation in the sense you can see that you can simplify that under a certain condition. when VGS dash is small compared to VP 0, okay, I can use binomial expansion for this. Okay. Now, if you use binomial expansion once only, 1 minus x to the power of n is equal to 1 minus n of x. If you just use that, you see if you get 0, everything will cancel out. So, I will use the second term also, that is 1 minus n of x plus n x squared by 2 factorial 2. Okay. That when you do, VGS dash minus 2/3 I am retaining plus 2 by 3 BP 0 into 1 minus 3 by 2 1 minus n of x, x is VGS dash by BP 0 plus square term 3 by 8. Now, you can see all the terms cancel out, VGS dash cancels, see these two terms cancel out. Okay. You will see all these terms cancel out and you are left with that quantity alone. Okay. So, that is actually you have got ultimately that term, last term, everything will go off. Okay. So, you will have this cancelling with that, no, nothing wrong, VGS dash cancelling with this term and this cancelling with that one. So, you are left with this term, 3 goes off, 2 by 8 4, 1 by 4, BP 0 into G naught into 1 by 4, BP 0 into VG dash square term. Now, see it is more pleasant thing to see. Plus, please remember, this is valid when VGS minus dash is small compared to VP 0. Very near to VP 0, it is not valid, it is small. Okay. Now, quickly finishing it off. So, IDS is therefore expanding that G naught by 4 VP 0. I have got VP 0 pulled out from there, that is VP 0, 4 is pulled out, VGS minus VT 3 whole square. Now, it is even more pleasant. So, it looks like our familiar equation for the MOSFET. What is this quantity? Expand that. G naught we write, it is channel conductance which is actually Q and D A rho L by A, sigma A by L. Sigma is that quantity, area W into A by L, that is G naught. And I have retained this term, and VP 0 is, and 4 is also there. VP 0 is Q in the denominator, Q N D A squared divided by twice epsilon r epsilon 0. So, it was sheer manipulation power, that is all, nothing more than that. So, now here you see Q and D will cancel with Q and D and 1 A will cancel with 1 A and 2 will cancel with 4, become 2. So, you will be left with mu n W epsilon epsilon 0 divided by A and 2 L, cancelling out that. Okay, we have, so that is mu n into this quantity. I just look back, you will see that this is the same equation, that is cancelling out all these terms, you are left with only that mu n into epsilon r epsilon 0 by A to W by 2 L. What is this equation? The very familiar equation of the MOSFET, mu C ox W by 2 L, VGS minus VT whole square. MESFET is not different from the MOSFET, only that you use the same equations to find the saturation current, and all that you do is replace the C oxide per centimeter square by CS. That is all. That makes a world of difference, because now we are talking of gallium arsenide, mu n will be higher. We are talking of CS instead of C oxide, CS is epsilon r. Okay, I think I will discuss this, continue on this, but you are starting from this equation, because this is a good point for a start in our next discussion. Okay, because now we can compare this MESFET with MOSFET, gallium arsenide MESFET with the silicon MOSFET. Where do we stand? All those things we can bring in by comparing these numbers. Okay, and when you take the transconductance, it will be these two will go. We will see that in the next lecture. Okay.